beginning of our story goes back to the days before the Civil War, when our ships and guns were comparatively crude, and the American Navy was dependent upon European designers and manufacturers for the production of its weapons. It was in those days that Admiral John A. Dahlgren, later Chief of United States Naval Ordnance, insisted that the resources of our own science and invention be applied to the development of arms and weapons for the Navy. The ideas of Admiral Dahlgren, nourished by American inventive genius and the advances of modern science, are now embodied in the U.S. Naval Ordnance Laboratory at White Oak, Maryland. This development is a unique story, a story of men of science combining their work in a common purpose. Here, over an area of nearly 900 acres, is spread a portion of our investment for the security of our nation. This immense plant of more than 70 buildings and equipment is an ultra-modern scientific center where up-to-the-minute ordnance research and development is carried on. Within these structures are some of the world's finest facilities for the conversion of ideas into realities, all aimed toward improvements in the Navy's weapons. The adaptation of scientific knowledge to modern ordnance is an intricate and highly coordinated job, requiring laboratories where test results and extensive research may be closely observed in all its phases, and where related details may be evaluated by a community of scientists and technologists. For such purposes, the Navy must concentrate not only on research in ships, in guns, and underwater devices. It must extend its research into the techniques of flight, into the secrets of sound, and into the unending mysteries of electronics. It demands more knowledge about propellants, about the behavior of weapons at supersonic speeds, about new methods of control, and new problems of flight into the stratosphere. Solutions to these problems are the mission of the new Naval Ordnance Laboratory. Its scientific findings must be coordinated with industrial production methods, providing in times of peace a basis of security, the assurance of superior weapons in any emergency. In a world now threatened by blitz techniques, super bombs, and guided supersonic missiles, the essence of security is foresight, competence, and speed. One of the important tools of research at White Oak is this giant betatron, which can assist the human eye to penetrate the mysteries of solid substances. Energized by 10 million volts, this tool enables scientists to study the internal structures of solid steel as much as 16 inches thick. For safety against dangerous radiation, heavy lead doors and thick concrete walls completely surround this powerful instrument. And automatic cutoff devices protect persons who might accidentally enter danger areas. Powerful probing X-rays from this huge instrument will safely penetrate to the innermost secrets of enemy weapons, as they have in this photograph of a Japanese aerial flare bomb. In the search for hidden defects in large structures such as welds and heavy castings, the betatron may reveal, as it did in this 8.5-ton anchor, a large gas cavity. Here is the famous supersonic wind tunnel building. Portions of its equipment were used by the Germans in perfecting the long-range V-2 rocket. It was modified by U.S.Navy designers at NOL and now includes 7 separate test tunnels of varying sizes. A radical departure from older types, it develops wind velocities by suction instead of by fan, and has made possible winds 5 times the speed of sound. Powerful vacuum pumps remove nearly all the air from this 52-foot steel vacuum sphere. At the opposite ends of the tunnels, where free air is collected and sucked past the model to be tested, dryers are set up to remove water vapor, lest in expanding in the tunnel, this water vapor freeze into snow and disturb the supersonic flow. There are 2 large tunnels and 5 smaller ones, all of them designed for various types of aerodynamics research. The huge vacuum sphere receiving the inrushing dry air extends upward through the roof of the building. The large tunnels, as well as the smaller ones, project through the building walls from the vacuum sphere and culminate in missile boxes, in which the actual wind tests are made. With a precision-built model set up in the working section of one of the largest tunnels, cameras record the reactions of a projectile. The behavior of rockets, projectiles, and new types of guided missiles can be studied by measurement of forces and a detailed examination of their shock wave patterns. It is expected that this equipment eventually will develop flow rates of approximately 10 times the speed of sound. By the use of an instrument called the interferometer, a somewhat different approach is made in the study of a missile's aerodynamic qualities. Here, the interference fringes of a projectile, shown by the camera, provide additional data for the scientist. Within this group of 12 buildings, set apart at White Oak, the Naval Ordnance Laboratory conducts its program of experiments in magnetic effects. These buildings are as free from magnetic properties as science can build them. Even the materials for bricks, sand, and mortar were screened for the removal of particles of iron oxide. The isolation of these buildings from disturbing magnetic influences is essential for the study of undistorted effects of the Earth field upon ship models and full-size weapons. After ordnance is wheeled into position for testing, a varying assortment of coils, carefully wound over that large framework, duplicates terrestrial magnetic fields. Magnetic fields which may be found under any kind of ship, on any heading, at any speed, in any part of the world. By such means, the magnetic behavior of new mines and new torpedoes can be predicted. The device you see here is not a bomb. It's called a bird. More specifically, it is the magnetic airborne detector, or magnetometer. It was first developed for the purpose of detecting submarines from aircraft. This uncanny instrument, when lowered on its cable, will spot precisely any magnetic variations from the Earth's magnetic field. Such variations are usually associated with oil and mineral deposits. Scientific exploration at NOL is also carried into the realm of plastics, where the search for new materials is an essential part of the development of new weapons. Modern ordnance continuously demands new materials with new properties. This woven glass cloth, for instance, is being cut to form a reinforced plastic shell. New synthetic substances now replace many previously essential strategic materials, chiefly metals, because of low production costs and because of changed requirements of design. Structurally, many plastics are ideal for highly specialized scientific uses, such as in magnetic devices, in electronic equipment, or in mechanical units. One new material which is now protecting millions of dollars worth of Navy equipment is the plastic spray which covers our zipper fleet. This was developed in the Plastics Laboratory, now a part of NOL. And so the weapon experts continue their rigorous tests upon these new substances with the hope of extending their usefulness even further. In the Environmental Laboratory of the plant at White Oak is a huge 105-ton hydrostatic pressure tank, a piece of equipment which can test the strength of ordnance under sea conditions at specified ocean depths. This huge cylinder, almost large enough to accommodate a Japanese one-man submarine, will reveal certain underwater facts about such weapons as torpedoes and mines, under conditions in which they can easily be observed. With its 40-ton hydraulically operated door, securely jacked into position, it can simulate water pressures encountered as deep as half a mile. The critical examination of ordnance in such simulated tests, where all interested scientists may readily study them, results in completeness of information and great saving of time and money. Also in the Environmental Laboratory are open seawater tanks, which permit the lowering of weapons to test their arming rates. There, NOL's scientists and engineers can observe certain facts concerning mines and torpedoes at simulated temperatures of Arctic, temperate, or tropical waters. Development and research in modern ordnance relies heavily upon expert shop craftsmen of all types. Precise machine tools must provide parts, some large and some small. Some machines shape the fragile parts of fiberglass for a secret weapon. Others mill out pieces for a fuse mechanism. In the shops at NOL, nearly 500 skilled artisans representing all trades and crafts, machinists, electricians, woodworkers, sheet metal workers, instrument makers, all combine their efforts toward accomplishing the basic mission of the laboratory, that of fashioning the parts and devices which will make U.S. Naval Ordnance second to none. Another concern of the scientists at the Ordnance Laboratory are the dangers involved in handling ordnance. The shock limitations of ordnance of any size must be thoroughly understood. This 75-foot drop tower is a test device where such possible hazards in the handling of bombs and projectiles may be determined and overcome. Fuses in large-sized bombs and projectiles may be tested by this apparatus. The test unit is hoisted to a determined distance, then centered over a steel-enclosed well 75 feet below the highest drop point. When the area has been safely cleared, the unit is electrically released from a remote control shelter. After the drop, the condition of the inert bomb, and particularly the live fuse, is carefully inspected by ordnance experts. Ordnance design and research is a complicated business, but the camera is one device at NOL which simplifies the scientist's job considerably. If a 1-inch steel ball were dropped into water, what would be its path and how fast would it go down? Normally it would look like this. But that happened too fast. You couldn't analyze it. So a high-speed camera is set up to run at 3,000 frames per second. It is turned 90 degrees on its side so as to show a longer path and furnish more details for analysis. If a cylinder were dropped instead of a ball, what would be its path and speed? By use of accurate models, performance characteristics may be determined which are of great value in the design of airborne ordnance. Speaking of design, there is an instrument used by the acoustic experts at the laboratory which actually makes designs. Patterns are formed by fine particles of sand dancing on a steel plate. These will fall in precise arrangements depending upon the frequencies of the driving mechanism. As the operator changes the frequency, the patterns also change into simple or more complex arrangements, since the sand particles come to rest at the acoustic nodes. This equipment is useful in establishing patterns for the design of underwater acoustic apparatus. In the study of sound, the anechoic chamber is leading Navy research to find answers to many unsolved problems, some of which have a vital bearing on modern warfare. Long fiberglass wedges, 30,000 of them fashioned to top, bottom, and sides of an insulated room, permit the study of sound in its purest form, with disturbance cut to a minimum. This establishment at White Oak, in essence, is the Bureau of Ordnance's new idea factory. But new ideas in weapons require the most positive of tests. For that, NOL uses the facilities of several field stations. At Hiwassee Dam, North Carolina, anti-submarine weapons are tested and evaluated. At Fort Monroe, Virginia, the entrance to Hampton Roads, mine actuation is recorded. Many types of ships passing over instrument-connected minefields furnish a variety of important data. At Fort Story, Virginia, rough water experiments and fire control tests are undertaken. And at Solomons, Maryland, airdrop and especially countermining measures are perfected. It might be said that the business of NOL is bigger and better explosions, but there is endless planning and study, design and evaluation which goes into the business of making explosions effective. The workers, the scientists, artisans, engineers, mathematicians, the draftsmen, representing diverse skills, trained in scores of technical specialties, all are working together as a team, perfecting the Navy's weapons, keeping strong her striking arm. Roughly 1/3 of a total of 2,100 employees are scientists and engineers. The relationships between military and scientific personnel at NOL are significant, since they provide a working balance between security requirements of the Navy and the scientists' need for freedom of action and thought. At the top of the military organization is an admiral, whose interest is to obtain for the Naval Ordnance Laboratory all the things it needs to operate effectively. Such an assignment is proof of the Navy's concern for the importance of ordnance design. The technical director of the laboratory is the civilian leader of the laboratory's scientific personnel. Dr. Ralph D. Bennett, former professor at MIT and widely known physicist and electrical engineer, is the senior scientist at the establishment and reports directly to the commander. One look at the auditorium during one of its seminars will give an idea of what is meant by professional development. Scientists and technical people require professional conferences in order to pool, evaluate, and prove their findings. With microphones amply distributed, all members can participate in the discussions. Seminars are considered part of the regular diet at NOL, and the auditorium is designed for such meetings. Library facilities also are an essential factor in scientific and technical research. Reference works, books, and periodicals in all specialized fields are centrally located. Staff members are encouraged to use these facilities for furthering their own professional reputations through publication of their findings. Also, those engaged in scientific work are not only given the opportunity, they are strongly urged to take active part in the activities of their professional societies, since such participation is measure of their professional interest in their chosen fields of specialization. In the training of junior scientists at White Oak, special classes are conducted as a supplementary program. Such classes often carry advanced university credit. Several of NOL's senior engineers and scientists serve as part-time professors at neighboring universities. This keeps them in close contact with advances in their particular fields of interest. Concern for the all-round welfare of each employee is part of the team idea at NOL, and this interest extends beyond the limits of the working day. The Employee Relations Division is responsible for many services to its workers. Assistance is extended through advice and information about school facilities and housing possibilities. A large map in the division office serves as a handy reference showing the residential distribution of all of NOL's employees. Another of the many devices which helps the Employee Relations Program to function quickly and intelligently. At lunchtime, an attractive and efficient cafeteria serves complete menus from a double set of steam tables. The large room will accommodate 400 at one sitting. But this same room is capable of changing its appearance for social functions. The scene certainly should be laid in Hawaii. But even though this is the NOL cafeteria, the party spirit has taken hold, and all members present are having fun. Social functions of this sort have contributed their part in developing a staunch feeling of group loyalty at White Oak. A variety of other recreational opportunities is also part of the important Employee Relations Program, such as some lively competition in the Great American Game, after work hours. A few lusty swats or even swings will do wonders for an appetite. But more than that, it really gets the fellows acquainted. And for the earthy and practical-minded, there is farming, small style of course, on the premises of NOL, where the diligent may till the soil. And in due time, what with some luck, they will reap their rewards for the family dinner table. All this adds up to better performance among the workers at NOL, who have a part in coordinating the hundreds of ideas, the hundreds of parts, the hundreds of tests in a piece of ordnance before it really comes to life. The achievements of the laboratory at White Oak bear worthy testimony to the worker's sense of personal responsibility and interest in his work. It was men like these and these, among a host of 2,000 others, who contributed to some notable achievements for NOL. Some of these were the development of a torpedo proving range using sound equipment, permitting the continuous observation of torpedoes under test, the development of influence field detectors for the location of submerged ordnance, enabling the recovery on test ranges of $60 million worth of equipment, the development of the first successful designs of anti-submarine proximity-fused depth charges. It conceived, designed, and tested the famous airborne mines which sank or damaged 2 million tons of Japanese shipping in the last war. It changed the 40-millimeter British anti-aircraft fuse by simplifying it for American manufacture, thus saving more than $100 million. This fuse brought down more enemy aircraft than any other fuse in the war. Also, in collaboration with the Bell telephone laboratories, NOL developed the magnetic airborne detector. This device is now exceedingly useful in surveys for mineral and oil deposits and in polar exploration. There is perhaps one more achievement which is NOL's greatest and its most promising. In the process of perfecting naval ordnance, NOL has developed a team of many professions, both military and civilian. It has advanced the dream of Admiral Dahlgren to where the United States Navy can have the superiority in weapons it deserves as a bulwark of a free people. The intensive application of science and technology to our nation's defense is the mission of the Ordnance Laboratory at White Oak. That is and will be the continuing NOL story.